Hello, class. Good morning. Okay, let's start. Given sufficient time. Okay. So is the screen visible to you? Yes.
Yes,
Yes,
ma'am.
ma'am.
Okay. So we have started the class yesterday, and today is the second class. This all we have discussed yesterday: course description and schedule, and other related things to practical. And you have been you must have got the all things which I have uploaded on the team. There you would have seen the sample practical reports, practical files.
Uh,
There you should have you
Excuse me,
seen? Yes? Yeah.
ma'am. We were added to the team later in the evening at 5 o'clock yesterday.
ओके कोई बात नहीं आपने देखा साइट को टीम को देखा आपने
हाँ जी, ma'am.
you can see all the things there the objective to tell you this is that in this sample practical file you will notice very good files. Okay, let me show that. It is important that you in your experiment list mention properly the objective, algorithm, code, output screenshots and analysis. Then the objective of the subject will be complete. You can see very good sample files. Last time I was taking the experiment lab. Then you see the sample files some of the students see, and here also you should have the conduction date and the submission. When you have actually done the experiment, there should be the good variation. Should not be like all the dates are same, and the submission means when have you submitted. It matters a lot, and you will see the difference in the marks. Then mentioning about the experiment objective program is this is the file which I have to delete. Actually there is something missing. Okay, in your class I have not deleted this one. In this file there is something missing. I should delete this file. You know, class is in continuation. If anything is missing, every time things cannot be completed. Course is really very wide, difficult to complete. But let's begin with. So here you can see, okay, objective mentioned properly, then algorithm. I will instruct to all the teachers taking the practical class that these all are mandatory, and that's why I have uploaded. And this is the code which you will run, and then you will see the output, then analysis. So this all basically completes the one particular experiment. These all the things are mandatory. They are for each and every practical. See, algorithm, then code, then output, and then analysis. So there must be the discussion for the analysis. Of course it will come from the theoretical part, but it is important to notice each and every step accordingly when you are running the code. Moreover, I will mention that what exactly the execution time is for the particular code. That also you can mention specific time for your code, how milliseconds it has taken. Okay, so in this way you will go for this. Okay, I have mentioned it for the name of the file element L2 because it is taking 2 lectures to complete it. Okay, so the first 2 lectures from the Horowitz and Sahni, which will be actually going to introduce about the algorithm, why the data structure is important for designing any algorithm. What I pointed out, that maybe you are getting the data structure as byproduct or end product of the algorithm. There can be any combination. Maybe the algorithm is simple, but the data structure is complicated with that. For example, you consider a linked list as a comparatively complex data structure than the array. So there is a relativity in context for the complication for the data structure, like you have the stack again through the linked list or simply using array, etc. So there can be combination of complicated algorithm and the simple data structure. Okay, so there can be any combination possible, that's not the point. Why to study data structure, we have talked about characteristics, we have seen. Okay, so sometime you may be asked the queries like you will be given the particular set of the instructions 1 2 3 4 and you are asked whether you can call it as a algorithm or not. In that case, these characteristics will help you to decide whether exactly this is algorithm or not. Can we call it algorithm? Here I have told one important thing, that maybe sometime the particular algorithm, let's say of 3 steps, is doing something perfectly, but in some other cases with some different inputs, maybe it is not going to give the desired outputs. And then in that case, to be very specific for the algorithm, we will say that okay, it is not the algorithm. Okay, so in this way, this is important, because in a general way you will say okay, it's the algorithm because it's having some steps and doing something, but to be very precise, in that case you have to be careful about the different characteristics which we have discussed yesterday. Then we talked about the pseudocode, when the algorithm is having the touch of particular programming language, and we call it as a pseudocode. And more specifically, the 2 categories you may have: iterative algorithm or the recursive. You are aware with this. When you have the for loop, you will say okay, it's iterative. And when you have a function where within the function it is called by itself, that will be a recursive one. We'll go into the detail. We talked about a one algorithm yesterday. The objective to discuss it, to give you the specific way to write down the algorithm. You may follow a particular pattern. You may follow this one or maybe some other. You can discuss if you have some other pattern of writing the algorithm in your mind. Okay, so here you have this, the term key algorithm, and then you are here with the name of the algorithm and the parameters which are part of this. Then with the comment line to explain about what it is, this what is a, what is n, telling about this, and then the logic for the objective is here to find out the max. So very simple code, just to have a beginning for the subject algorithm. And now your attention must be towards the algorithm way of writing and the analysis and all that. Okay, now here in this slide I discussed about the particular algorithm for the selection sort, and this is also for the selection sort. Here you should notice that when you write the algorithm or when you start solving any problem, maybe your algorithm will come in this form. If you talk about the selection sort, I don't think method is required to discuss over here, but broadly, you know, in case of the selection sort, whatever the data is given to you, you select the smallest one and put at the first position when you have to sort it in the ascending order. Okay, so your 51 will be coming over here. Interchange is required because you have to keep your all the data with you. You cannot just copy 4 here, then you will be having 4 here and 4 here, then 51 will be lost. So what is happening, you go for interchange between the two. because your order is in ascending. Okay, if you are going to go for this descending, then of course you will be finding the largest and then putting that at the right first position. Right position is the first position in case of the descending order, so interchange operation is required with the max. Otherwise interchange is required with the minimum element. And similarly you will go for the similar process for rest of the elements, right? So this process is mentioned here with the help of this particular algorithm. And as I told, pseudocode and algorithms sometimes may be used interchangeably, but very precisely you should know what the algorithm is and what the pseudocode is. Like here you are using the for loop directly instead of writing for the values 1 to n for a variable I. You may use English like statement, but it is used here for loop, which is telling about in an English like statement that you examine now beginning from the ith index, like initially from 1 to n, then next time the value of I will be 2, then it will be checking for 2 to n. For example, here I told to check from 0 to 4, and then once this location is fixed, then location is fixed with the perfect value, then you are checking the values from 1 to n, and similarly then 2 to n, and then from 3 to n. That's why you have this loop here. And then you are mentioning English like language simply that you are examining the elements from beginning to end and finding the smallest element. Wherever it is, if it is at the jth index, you are interchanging the. So there is no statement directly which can help to the program developer to convert them directly as a code. Just simply return interchange. How to do the interchange and how to find out the smallest element. These two operations can be mentioned separately or with the function for finding the smallest one. You may have another function, let me say you have may name that as f1, and another function which is performing the task of interchange. So you may develop this type of the code using the two functions, and maybe with the one you may design it anyways. So as a practical point of view, I would say that selection sort must be developed using the functions, and the another version where here itself within the body you are mentioning the complete logic for finding the smallest and finding the for interchange operation. This you see the general logic for the interchange with the help of the third variable, the one statement, then second statement, this is the third statement. No need to discuss, I think you must have used it many times earlier. Okay, as a scope of the subject, I would like to mention here that you may have the varieties in the algorithms, but when we talk about the examinations and scoring the good marks, you better to present either directly the such type of the algorithm so that teacher can know that you have the idea about the perfect logic. Okay, if you cannot do it at once at the initial stage, then you may mention these two, right? Because the stages are there for doing something. So but this should come up on the paper that the logic is should be visible to the teacher. So here it is, you may develop another code without any function, and here with the function, and this is. So in this way you have the two experiments to do. We talked about the performance analysis also, and there we talked about you have the two possibilities, either go empirical analysis. This is all about when you are really experimenting and observing the time and the space requirement. Okay, so yesterday I discussed about it completely. Then mathematical analysis is there, where you are before actually implementing and running the code, you are using the mathematics, different functional values, expressions, and the standard functions relation with the function which you have got for time and the space requirement. So mathematical analysis, and we will be focusing for the mathematical analysis in the lecture class. And for the lab, as I told that you should observe the actual time taken by the code when you run it. So in that way you can be dealing with both the things together in the class with the mathematical, which will also be the part of your lab report and empirical analysis observing exactly the time. Code blocks itself gives that how much time it has taken. So you may use the compiler which is directly giving the time, and then you have a very good tool with you when you get the time directly through the compiler by making the changes in the code. For example, the using the actual data which is to be sorted and random data, and then the data which is going to take maximum time. For example, if you have to sort the data, if you have to sort the data in ascending order, okay, but you have used the data completely in descending order, so it is really going to take the maximum time. That is the worst case. So you can play with the code, experimenting with the types of the data and then observing the actual time it is taking, okay, which is true with the help of the mathematical analysis also. So in that way you are actually checking the mathematical analysis and verifying that through the actual time requirement with the help of these three types of the data. Okay, you are aware with that, the best case, average case and the worst case. We will discuss it again as the topics will come. Performance analysis of the algorithm is actually to get know the answer of few questions. One is, does it do what we want it to do? It's very simple, and you see, like unconsciously you are looking for every algorithm with this, right? Does it work correctly according to the original specification? That is what the problem is expected to be for solution, what the problem is asking for. Is there documentation? Is the algorithm really documented well? Is also one of the characteristic for the algorithm. For example, you have seen the comment line for explaining the parameters in case of the selection sort here. It is here, yeah, this. Okay, so this is also one of the characteristic. So if you are given the 2-3 algorithm and you are asked which one is the best one, you should be capable to do that after this lecture. Okay, and are the procedure created in such a way, you see the way, method, steps, that they perform logical functions. Okay, are the functions designed well, which are easily understandable and in the form of the way the problem is asking for the solution. Okay, that is how much clearly that is representing the logic. This point is for that. Is the code readable? This is also important. You see, when you are writing any particular code, that should be understandable. It matters that how the handwriting is and how you have maintained the space, how you have maintained the indentation. Okay, sometimes you let me tell you about the Corman. Corman is not using the brackets. Okay, you have a code from here to here. What it is doing, it is maintaining the indentation. यहाँ bracket नहीं होगा, बल्कि क्या होगा, some code, a part of the code is here and then maybe some other part of the code is here. So maybe this is the complete book page, then there is an indentation only this much, okay, which is clearly understandable to the student that okay, it is from here to here, but the brackets are not there. But because of indentation, left में जो space बचा है, because of that you are able to understand this is the one block of code and this is the another one, okay, where this bracket is not mentioned, okay, but the indentation is more in comparison to this one. So in that way the blocking of the code is done instead of the open curly brace and the closing curly brace. So these are the different ways, but whatever be the case, you use the bracket or don't, that should be clearly giving the understanding to the reader. Okay, then moving towards this time and the space complexity. Analyzing the algorithm, let us start the important part of the, that was like a revision of the yesterday's one. Okay, I tried to revise because I know many students got added yesterday evening only because of the section information was missing, so we were managing to get that, that's why it got late. Okay, so analyzing the algorithm. You see, don't take it in a very simple way. Okay, we will use asymptotic notation. That will be the complexity, and that is the analysis. Just give the importance to each and every point here mentioned. You see, as I told, in case of analyzing, you are interested to know about how much time and how much space it will take. You will see in the next slide the kind of definition also. So predict the amount of resources required. Whenever you have an algorithm, that is with the objective for implementing, for making the code. So that is really going to use some resources. And the resources are specifically to how much memory is required to run that particular code, which is based on the specific algorithm. And what is the computational time? How fast the algorithm runs? Is it slow or fast? Objective remains towards this. Not only, okay, it is going to take this much time. Is it slower? Is it faster? That also matters, with the purpose to compare the two different methods for the same task solving. Okay, so what is the fact? Running time grows with the size of the input. The fact is written like this. It does not mean that it always grows fastly or slowly. Here the point is written, time grows. Whenever the size of the input increases, of course the processing time will increase. But whether it is increasing very fastly or slowly, it matters. Means maybe the size of the input was initially, let us say 4, and you may keep the example of sorting in your mind, sorting, okay, and then for the same algorithm we are using another time, the size, let's say 24. Okay, so this is the initial size of the data, and this is the at the next stage the size of the data, and let's say the time taken. Okay, let me write down. Time taken with this is, let's say, 2 millisecond, and time taken by this is your, let's say, 10 millisecond. Okay, so how much is the change in the time? There is a difference of 8. Okay, maybe some other algorithm is there. With that we have the data size 4 and then 24, and with that algorithm for the same task there is the time requirement here, let's say 7 millisecond, and for that it was, let's say, 2. Okay, so there is a difference of 5. So this is to be noticed in case when we talk about the algorithm analysis, that what is the rate of growth for the time when the size of the input increases. So relatively we will say, okay, it's better to use this algorithm, because when we increase the size of the data, it is having a less impact and it is having a more impact, because we want the algorithm should be good, scalable. Okay, the scalability of the algorithm should be good, and that is, okay, are you getting? So this is the time grows. Here the point to be noted for fastly or slowly. So this is the subject actually. In algorithm analysis we look for it, right? So with this fact we are able to compare with the help of noticing the slow growth or the fast growth. That is why there is a topic, rate of growth of the function is also important. Rate of growth of function. Okay, rate of growth of function. Okay, rate of growth of function. Okay, so this topic is also important because it helps a lot to compare the different algorithms. Now let's talk about the input size. There is a number of elements in the input. It is concerned with it, whatever will be the number of elements in the input, the size of the array will be dependent on that. Polynomial degree. Polynomial degree, it is the term which is talking about how much there is a growth, polynomial growth or the linear growth of the elements in the matrix of the bits binary. Okay, you binary representation of the input, size of the every element is how much big, but that remains comparatively fixed, kind of constant, so it doesn't matter. What is the energies of the graph? Just a specific example is added up here. We may be more just concentrating towards this, whatever I discussed about this. Okay, so running time is actually proportional to the number of primitive operations executed before termination. How much time the particular algorithm will take, the meaning of this is when you implement it, which steps will execute, because in a particular algorithm, depending on the condition, some of the steps may be missed because the condition is not true. So actually how many steps are executing, that decides the time of execution. So very general common fact, but the point to be noted for the steps, the count of the steps matters. Okay, this thing will go ahead when we will go for the analysis, right? Arithmetic operations take some time, data movements takes the time, maybe you are assigning the values to different variables and interchanging the values, some other variables are coming into the picture. Data movements, control, that is the for loop, etc. you are taking, conditional statement, if and while, etc. is there, and yeah, comparative operations. So these are different operations which are taking place in different steps. So all the steps are taking some time. And if you have an algorithm having all these things there, then we pick up that particular operation which is comparatively taking more time than others. Out of all these, the comparison operations, if we have some sorting process, then comparison operation takes more time than other operations. Then we may just leave all those, like considering taking the constant time, then comparison operation is given the emphasis. We keep the example of the sorting, and the comparison operations are clear, then we may develop a expression for finding how much comparison operations will be there. Based on that expression, we decide the complexity. Okay, so analyzing the algorithm. Now I have pasted here some of the book content so that you feel comfortable when you start reading the book yourself. At least first chapter you should read line by line. That will give you the good strong foundation for the subject algorithm. Okay, so this I have already repeated many times, and in data structure also you must have seen. Space complexity of the algorithm is the amount of memory it needs to run the up to the completion. Okay, why I have pointed out here, because at the time of the running there sometimes comes different variables into the picture, so the size of the space requirement increases, while when you see this simply directly the algorithm, you may not see the actual need of the space. So whatever is the space required to complete the running of a code is the space complexity, and the time complexity of an algorithm is the amount of computer time it needs to run to completion, that is how much time it took for the running. Now here, when the program run, before that there is a compilation process also that is missing in it. It's only the running time. It does not include the compilation time. Okay. Performance evaluation can be loosely divided into the two major phases. You see here, it comes the kind of variation for the discussion I made here. See here in this slide, empirical analysis and the mathematical. It is told here in this discussion in a different way. Both the things are same. This is the priori estimates. That is when you are not running the code. It's on the basis of mathematical equations you are judging the performance of the algorithm, complexity of the algorithm. And this is post-write testing, that is when you are running empirical analysis kind of, okay. So we refer to these as performance analysis and performance measurement. There is a very slight difference in the term. When you are very particular for the technology, then you see the performance analysis is as the primary estimates with the mathematical analysis term is there. And for actually when you are doing the empirical method, you say performance measurement, you are actually measuring the time requirement and the space requirement. So the performance analysis and the performance measurement. Okay. So space requirement and the time requirement, we will focus today for the space complexity. Space complexity, that is how much space it will need to run till completion. Okay. So in mathematical form, space requirement can be represented with the two terms. One is here, you say the SP, space requirement of the particular program. P is C plus SP. C is a constant part. Okay. C is a constant part, constant space requirement by the particular algorithm. Okay. Fixed one, which is not going to change. And SP is the variable space requirement by the particular algorithm. Very simple to understand. If you have an algorithm to sort and you are taking the size from the user, that n, maybe sometime he is giving the size of the data 4, sometime it is going to give the size of the data 40, sometime 80. Okay, so this is the instance characteristic. At a particular instant, how much data size is. So it's a variable part. So constant part and the variable part. Okay, C is constant. So space complexity, concentration, for the space complexity, we give the concentration for the variable part SP, because constant is like a fix. Okay, and our objective is to go to see the rate of growth, which depends upon the instance characteristics, which is the size decided at the time of running. Okay, so you represent the complexity with the combination of the two, C plus SP, which is the variable part. So this all discussion you will see in the book, so don't feel yourself bored when you see the book. You will see all those things here. So partly just you can see, which I discussed here. A fixed part that is independent of the characteristics, for example, number, size, which you input at the time of running, independent of, always fixed. Program book, anytime when you run, some size of the requirement, some size space requirement is fixed. Okay, this part typically includes what? Space for the code. Okay, space for simple variables, they are fixed variables in the code, fixed sized component variables. Okay, the variables which are fixed, for example, some part of the array you are always using, and a particular specific array of a specific size. So fixed sized component variables, space for constant, and so on. That can be easily judged with the code, where you can say, okay, this much of size is the basic requirement for the code, which is not going to change. You run it 100 times, 1000 times, whatever. But at every time, if you are getting the size input from the user, that is going to change, which I have explained here. So those are termed as the instance characteristics, that a variable part that consists of the space needed by the component of variables whose size is dependent on the particular problem instance, okay, being solved. The space needed by the referenced variables, depending on the condition, maybe you are jumping to some other function, calling to other function and executing that. In that case, the space requirement is the instance characteristic. Okay, it is not fixed. So this is also coming into this part, variable part. That is to extent that this depends on instance characteristic. Particular moment में क्या data है, which function will be there, if new function will come up, depending on the condition, the space requirement will increase because there will be the variables, the space requirement will be there. And the recursion stack space, when you have a recursion concept there, then the stack space is required to store the return addresses. Okay, whenever there is a call to the function or there is a recursion, there is a stack space requirement to store the return address and to store the temporarily the values of the variables which will be used later after coming back to the main function from where it is called. Okay, so in that way some instance characteristics, you will see the term instance characteristics for variable part किसी instant किसी moment पे depend करता है. So these two things, depending on these two, you explain the or you find out the complexity of the particular algorithm. You can see the example here. Okay, so after all this I told, let me give you a 1 minute time to have your own observation and looking the statement. This is all from the Horowitz and Sahni, that how to get the space complexity. Okay, so just give your attention and let me know, could you get anything, because each and everything is mentioned over here. Are you hearing? I'm continuously talking because I have to be fast, because I want ये सब चीजें आप थोड़ा पढ़ भी चुके हैं, तो we have to reach to the exactly to our unit 2. So if you have any problem in between, you are supposed to ask. Okay, you will be answered for your query. Yes, any one of you so far, any query? Okay. This is the algorithm of just, you can say actually the one line algorithm. It's simply name particular term algorithm. This is the name of the algorithm. These are the variables, parameters of this algorithm. It's only calculating the value of this particular expression with the help of these values A, B and C. So there is no instance characteristic, variables are fixed. So there are 3 fixed variables A, B and C in it. That is, the space needed is independent of the instance characteristic. So आपके पास में जो ये part है, this is actually ये SP. Okay, this, when you see here, actually let me now change it. C SP within the bracket, the same notation which you have used here. It is C plus SP. Okay, so in that case the constant space requirement is for the 3 variables. Okay, so constant part is constant, you may just say okay constant. So S, your this SP, your this SP is equal to C, only C, just a 0, because this variable part is 0, कोई है नहीं instance characteristic. In that case, just this time remember the constant space requirement is represented with this big O notation 1. कोई बहुत नया तो नहीं है, थोड़ा आपने देखा हुआ है, TOC में भी मैंने डिस्कस किया था और डेटा स्ट्रक्चर में भी डिस्कस हुआ. Constant space requirement and the time requirement is represented with this big O1. Okay, it represents actually the constant space requirement. So in this way you can explain the complexity of the space complexity of any given algorithm. Another example for you, this one, the algorithm is for sum summing the series of the numbers. Initially the variable s is assigned 0, you know that, and here you have a loop and expression s is equal to s plus ai, you know that. I don't think there is a problem. You are able to add a series of numbers beginning from 1 to n. Okay, so instance characteristic is what here, n. How to judge for it for the constant and the variable part? There is variable n which is an instance characteristic which may change, maybe 2, 10, 20,000, 1 lakh. That is the value which will be given at the runtime. So the instance characteristic is the variable n. So SP, this variable part can be given by this way, that always you will find the space requirement for this algorithm is n, specifically this much of numbers, then plus 3 is mentioned over here, will be greater than equal to 3. Why greater than where term is there? Because that space will be required with the statements also. Okay, storage space for the code, so greater term is there. And for this, whatever will be the array, and one space requirement for itself the variable n को स्टोर करने के लिए भी तो स्पेस चाहिए, and the space requirement for I and the space requirement for the variable s. So in general you can say the complexity is greater than equal to n plus 3. If you go with the notation, then you can simply write down this order of n. For this, when we will see the asymptotic notation, I will be giving you this idea that whenever you have any mathematical expression, for example here it is n plus 3, so whatever is the highest order term, that will be used here. Okay, if you would have been something like that, n square plus 4n plus 2, for example, then in this case you would have said that the space complexity, even the time complexity also, if you represent in terms of big O notation, you would have said order of n square. Asymptotic notations we will discuss, but you can just accept this concept because will be used everywhere. Okay, so the complexity is of order n, or the complexities of order, and it's just a separate mathematical part I told to you, right? So finding the space complexity is simple. You have to give the observation to each and every statement, right? Now you have another one for your practice. The space complexity is to be observed for this code, where you are finding the recursion process. R sum is called, and it is actually the function itself. The function is calling to itself, so we will say that's a recursive function. So how to find out the complexity of this? You will start observing the variables, and then you will start looking towards how many variables are there, then how many are there, then looking towards the space requirement for each and every variable, and then out of those variable which is instance characteristic, which is depending on the runtime, which is changing every time depending on the value given at the time of running. So these observations are to be given. So there is variable, you are finding variable n, which is an instance characteristic and is always an instance characteristic. That is the, maybe it is used differently, so you have to give the attention to the code. That is the value given at runtime, so we are saying it's an instance characteristic, that is a variable one. Okay, variable one, that is SP में variable part को deal करेगा. You have the space requirement by the particular program. SP is equal to C plus variable part requirement is mentioned by this way. You may use another way also, another variable also, not a problem, but book is using this one. Okay, so there is a recursion at step 3 you are observing. So space required for formal parameters. Now do you remember the actual parameters and the formal parameters in case when you are using the functions? Yes, anyone? Actual parameter and the formal parameter. Which variable is termed as the formal parameter and which is termed as a actual? Yes, I am giving you time. Okay. Local variables, that you know, the variables within the function, and the return address. You are finding these things here. The space requirement for the formal parameter, the space requirement for the local variables, the space requirement for storing the return address. As I told, the stack is used for that purpose. Okay. Yes, formal parameters and the actual parameters.
मैम जो फंक्शन कॉल में हम पास करते हैं पैरामीटर वो एक्चुअल होते हैं और जो फंक्शन की डेफिनेशन में होते हैं वो फॉर्मल।
जब हम वैल्यू पास ऑन करते हैं जिसमें ठीक है वो एक्चुअल है, एंड व्हेन यू आर जस्ट यूजिंग एज ए, यहाँ पर कैन यू जज विच इज द एक्चुअल एंड विच इज द फॉर्मल?
मैम जो फर्स्ट लाइन में है ए कॉमा एन वो मैम फॉर्मल है।
Formal, because the value is not fixed, there can be passed any value to them. Okay, otherwise here you will be using the values, here the values will come up, right, directly.
यस मैम।
Okay. So space is required for all these formal parameter, actual parameter, return address. Why the return address? Because whenever the function is called, it has to return back. Okay, after completing the execution, the call in the call function. So return address is also required. So assuming the return address require one word of memory. So it is actually we talk about the space required in terms of the word, or it's like a bytes. Okay, simply a general notation, one word. There can be any number of bytes with that. So each, now another point, each call to rsum require at least 3 words, 3 space requirement. Okay, 3 word space requirement whenever there is a call to rsum. कौन से हैं? You need a space for the variable n, a return address, and a pointer to array. Okay, because array is in the picture and you are using the recursive process, so array is to be accessed, and for that there is a pointer variable which is used to access the values from the array. Recursion depth, अब ये recursion आप लोगों का डेटा स्ट्रक्चर में प्रॉपर्ली डिस्कस हुआ था. Have you studied the recursion process? I consider, you know, data structure is a prerequisite for this subject. I consider that you know it, otherwise you will ask your doubt. So I am not going into the detail for this. Okay. So recursion depth is n plus 1. For example, I have given here the example also. For n is equal to 3, rsum depth क्या है, कितनी बार आपका rsum run करता है. Okay. So for this specific value, you will see this code and find that rsum will run for the value 3, for the value 2, for the value 1, for the value 0. Why? Because it is here the condition n less than equal to 0. It runs for 0 also. So for the value n equal to 3, how many times it has run? 4 times. 3 वैल्यू थी, 4 टाइम्स रन किया तो क्या हुआ, n plus 1. Okay, when the value of n is 3, it has run for 4 times, so recursion depth is n plus 1. Okay, so this much of times there will be the need of space for 3 variables. So 3 into n plus 1. Constant part को ignore कर दिया, no problem, constant can be ignored completely. So we have the complexity of order n, because it is going to give you 3n plus 3, so of order n. Okay, so in this way you will work out for the space complexities. And now you can see here this table where you will see I have used this notation that whenever there is a constant requirement, you will say the complexity is of order n. Constant space complexity occurs when the program doesn't contain any loops, recursive function, or call to any other one. That you have seen with the example also. And when the order of the complexity is this, then you say it's a linear space complexity. That example also you have seen. These all techniques you have already studied and we will also discuss, but the space requirement for these is given like constant requirement, constant requirement, constant requirement. And here the merge sort is having the complexity of order n, and in case of heap sort also of order n, 1, that is constant. So just to keep this constant concept in your mind, this is a fixed concept, that whenever there is no variation in the space requirement, a constant one, you say the complexity is of order 1. And where there is a possibility for change in the size, this is a complexity. Okay, so in general it is this, but you have to go for representing the space complexity in such a way for each and every statement and explaining the space requirement, and then accordingly getting some expression and then representing that in asymptotic notation big O. Okay, in case of the space, big O is sufficient to represent the complexity. So here I have completed this space complexity topic today. Next time we will give more attention towards the time complexity, and every time for the time complexity. Okay, space complexity concept will be easily applied and you can easily get. Okay, fine. So class practice assignment based on these two lectures L1 and L2 will be like defining the algorithm. You should be clearly able to define, and you should be able to give the characteristics and judge the algorithm, and you should be able to write down the algorithm for any given task, and you should be able to find out the space complexity. So accordingly you will get some class practice questions from me. Okay, so this is all for today, and you can just ask if you have some query. I have just 1 minute left with me. uh, I'm taking the attendance downloading now. Okay, yes, any query, Avish?
No.
Okay, and just accept the thing that I will be fast, because now you are in third year and we have to cover the syllabus that helps you to understand all related important concepts of the subject. So we will try to complete each and everything. So just go through after the classes and come back with your queries in the next lecture. Okay, you may do that. Okay, bye.